Good afternoon. Is the screen visible to all?
Yes, sir.
Okay. So in the last lecture, we've seen that theorem that if V be the direct sum of all the subspaces, then there exists a k-linear operator. Okay, E1, E2 up to so on Ek, such that this whole condition holds. Okay, and vice versa. Conversely, if Ei are the k-linear operator and also satisfies four properties. Which one? 1, 2, 3, 4 statement. Then V is equal to direct sum of all these subspaces. Okay, so this is the proof of the theorem. Now, the next theorem, next point is invariant direct sum. Okay, what is the meaning of invariant direct sum? Okay, wait. Invariant direct sum. Invariant direct sum. Okay, now look at it. Suppose V is equal to W1 direct sum of W2 direct sum of up to so on WK. Okay, so now this is WK and each WI. Okay, this WI and each WI is invariant under some given linear operator T. Is invariant under some given linear operator T. Okay, operator T. Then this is the invariant direct sum. Okay, what is V? V is equal to W1, W2 sum of all these direct sum of all these subspaces, and Wi is invariant under T. That means suppose this one is V, and this is the codomain V, and T is the linear operator. Okay, suppose this is W1, this one is W2, can up to so on. This is WK. So what is the meaning of invariant? For alpha belongs to Wi. If this T of alpha belongs to Wi, then this Wi is invariant under T. Okay, get it out. And V is equal to all this direct sum of all the subspaces. Then this is the invariant direct sum. Okay, so the next step is for such a decomposition of V. Okay, so this is the word decomposition of V. Okay, ते काय केले ते तुकडे पडले त्याचे W1, W2, so on decompose झालाय हा V. Okay, so for such a decomposition of V, T induces a linear operator T1, T2 up to so on Tk. Okay, for such a decomposition of capital V, this T, okay, induces a linear operator. Which one? A linear operator T1, T2 up to so on Tk. Okay, on W1, W2 up to so on this Wk respectively. Okay, we know that what is a restriction of T over W. Okay, we know that which one. Suppose this is the V is the vector space and T is the linear operator on this is the linear operator on V. Okay, and suppose this one is W. Right. This is the Wi, suppose. Okay, so what is the restriction of T on Wi? So this is again Wi. Okay, and this is what T of W. Okay, what is T of W? T of W of alpha is equal to T of alpha for all alpha belongs to W. Is it correct? That means for each and every vector of W, alpha belongs to W, this TW is coincide with T. म्हणजे हा जेव्हा टी जेव्हा डब्ल्यू आय वर अप्लाय होतो तो काय होतो टी डब्ल्यू ऑफ अल्फा. सो दिस इज द वॉट रिस्ट्रिक्शन ऑफ टी. Restriction of T on WI. Okay, this one is WI. Okay, we know that this one. Okay, what is the restriction? काय केलं रिस्ट्रिक्ट म्हणजे काय केलं तर डोमेन त्याचा रिस्ट्रिक्ट केला. या टीचा डोमेन रिस्ट्रिक्ट केल्यानंतर काय आला डब्ल्यू आय. सो इच वेक्टर ऑफ डब्ल्यू आय टी ऑफ डब्ल्यू अल्फा टी डब्ल्यू ऑफ अल्फा इज इक्वल टू टी ऑफ अल्फा. Okay, so this is the restriction of T on WI, that is TW. Okay, we know this one. So for the such a decomposition of V, T induces the linear operator. So here W1, W2 up to so on WK are the K subspaces of V. Okay, so each subspace we get one linear operator. Okay, हा जर W1 असेल तर हा काय होणार restriction of T on W1. ह्याला नाव दिलंय T1. Suppose this one is W2. Okay, मग या सबस्पेसवर काय येईल तुमचा रिस्ट्रिक्शन. Suppose this is W2. This is TW. That is TW2 now. Okay. So here, look at it. For the such a decomposition of V, T induces the linear operator, this one. T1. This is the restriction of T on W1. This is the restriction of T on W2. Okay, and similarly up to so on WK. Okay, any doubt up to here?
No, sir.
Okay. If suppose alpha belongs to V, it's any vector. If alpha belongs to capital V, it's any vector. Then, what is alpha then? V is the direction of all the subspaces. That means we can write this alpha is equal to alpha 1 plus alpha 2 plus and up to so on. This is alpha k, where each alpha I belongs to Wi. Okay. So what is T of alpha? Apply this operator on alpha. So what is T of alpha? So this is T of alpha 1 plus alpha 2 plus up to so on. Wait a minute. Plus alpha k. Okay. So that implies T of alpha is equal to T of alpha 1 plus T of alpha 2 plus up to so on. This is T of alpha k. Why? Because T is linear. Okay. Now, this alpha 1 belongs to what? W1. This alpha 2 belongs to W2. This alpha k belongs to WK. Okay. So, this T induces the linear operator. Which one? TW1. Okay. Of alpha 1. हा T कसा अप्लाय होतोय W1 वर TW1 आपल्यासारखा अप्लाय. Okay. Plus this is TW2 alpha 2 plus up to so on. This is TWK alpha k. Is it correct? Any doubt?
No, sir.
Okay, what is T of Wi? T of Wi, TWI is the restriction operator on Wi. The restriction of what? T on Wi induces by T, that is induces by this T. Okay, so hence instead of TW1, TW2, write that TW1 is equal to T1, TW2 is equal to T2. Okay, so this T of alpha, this implies this T of alpha is equal to T1 of alpha plus this is T2 of, sorry, this T2 of alpha 2 plus up to so on Tk of alpha k. Okay, denote. What denote? T of Wi is equal to Ti. Okay, so in this way, we say that T is the direct sum of, look at here, T is the direct sum of the operators T1, T2, and up to so on Tk. Okay, any doubt up to here?
No, sir.
And this TWTIs, obviously, wait, obviously, these TIs are not linear operator on V. कसा आला हा? T linear आहे पण TIs are not linear on V. Why?
Is restriction.
येस 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 करेक्ट. हां, टी आय कोणावर आपले ऑपरेट केलं आहे? डब्ल्यू आयवर ऑपरेट केलं. ओके, टी आय इज दी operate domain of the TI is what? WI, not V. Okay, we don't know how this TI work on element of V. Okay, okay, if alpha belongs to V, then I don't know this TI how कसा operate होईल हा मला माहिती नाही. Okay, but we know this TI how operates on WI. Okay, TI of alpha is equal to T of alpha for all alpha belongs to what? W. Okay, हा linear आहे म्हणजे मग इथे हा linear असेल. But for alpha belongs to V, we don't know how this TI works. Okay, so that's why here TI are the not the linear operator. Okay, on V. ऑपरेटर कशाला म्हणतो आपण? ज्याचा डोमेन आणि कोडोमेन सेम असायला. इज इट करेक्ट?
Yes, sir.
लिनियरचा जाऊ द्या. ऑपरेटर कधी म्हणतो आपण? When the domain and codomain is same and which is linear. Okay, so what is the domain of TI? WI, na? Okay, so it is linear on WI, but not, sorry, linear operator on WI, but not on P. Okay, any doubt?
No, sir.
Now, the next theorem is, ओके, थेरमकडे लक्ष द्या. सगळे थेरम एकासारखेच वाटते. ओके, एकसारखेच वाटते स्टेटमेंटकडे पाहून, पण आहे डिफरन्स आहे. ओके, नेक्स्ट थेरम. Let T be a linear operator on vector space. Let capital T be a linear operator. A linear operator on vector space V. Okay, and this V is equal to what? Direct sum of all the subspaces W1, W2, and up to so on WK. Okay, and also there exist there exist k linear operators. K linear operators E1, E2, okay, and up to so on K on V such that first condition each EI is projection on V. Each EI are projection on V. Okay, second one, EI into EJ is equal to 0 whenever I is not equal to J. Third one, I is equal to E1 plus E2 plus up to so on K. Okay, and the fourth one, range of EI. Range of EI is
WI.
WI. Okay, हे तुमचे सगळे given statement आहे. Okay, all these things are given. Now, the necessary and sufficient condition. Then necessary and sufficient condition. necessary and sufficient condition that each subspace WR subspace WR, okay, is invariant under T. Is invariant under capital T. Is that T T commits with each of projection here. Each of projection EI. Okay, that is we have to prove that T into EI is equal to EI into T. Okay, what is the given things? Let T be the linear operator on a vector space, and V is the direct sum of all these subspaces. Okay, and is all the fourth statement which is given to us. Okay, first, second, third, fourth, and there are k linear operator on V. Okay, and the necessary and sufficient condition is that each Wi is invariant under T. Is that T commutes with each of the projection EI. Okay, so in the first part, we are going to assume this W is invariant under T, and we have to prove that T into EI is equal to EI into T by using all these given things. And in the sufficient part, we have to assume which one? Wait a minute. Necessary and sufficient condition. The first thing, in the first part, we have to assume that this one, T into EI is equal to EI into T. That is sufficient part. Okay, and we are going to prove Wi is invariant under T. And in the necessary part, we are going to assume this one, Wi is invariant under T, and we have to prove that T into EI is equal to EI into T. Okay. Now look at the proof. Okay, first prove the sufficient part. Okay, प्रत्येक वेळेस आपण necessary part करतो prove आधी sufficient part. Okay, sufficient condition. हे तरी कळतं का नाही कोणतं sufficient condition आहे कोणतं necessary आहे. Okay, which one necessary part? Assuming Wi is invariant under T, we are going to put P into EI is equal to EI into T. This one is which part? Necessary part. And what is sufficient part? Assuming T into EI is equal to EI into T, we have to prove that Wi is invariant.
Wi is invariant under T.
So here sufficient part assume. Suppose a linear operator T, linear operator capital T commutes with each EI. Okay, that means T into EI is equal to EI into T. Okay, for all I running from 1, 2 up to so on. Skip. Okay, give it as an equation number 1. Okay, and we have to prove that each Wi is invariant under capital T. Okay, look at here. Let alpha belongs to Wi in any vector. Okay, alpha belongs to Wi is any vector. If we prove P of alpha belongs to Wi, then Wi is invariant under T. Is it correct?
Yes, sir.
Okay. So look at here. Let alpha is the belongs to wi be any vector. Okay, not alpha I म्हणतोय मी, अल्फा म्हणतोय. अल्फा हा कोणताही वेक्टर आहे डब्ल्यू आयचा. तर तुम्ही अल्फा आय म्हटलं की डब्ल्यू आय मध्ये जाणार तो असं म्हणतो. Okay. Here the alpha belongs to wi be any vector. Then the definition of ei on wi we have what we have this ei of alpha. What is this one?
Alpha I.
अल्फा आहे नाही, अल्फा तेच सांगतो मी, कारण की अल्फा तुमचा डब्ल्यू आय मध्ये आहे, त्यासाठी सांगितलंय नॉट अल्फा आय बिलॉंग्स टू डब्ल्यू आय. ओके, अल्फा दिलाय तुम्हाला इच त्याच्याऐवजी. ओके, अल्फा व्ही मधले नाहीये तुमचा, अल्फा डब्ल्यू आय मध्ये. ओके, असं काय घेतलं, इफ वी प्रूव्ह दिस स्टेटमेंट पी ऑफ अल्फा बिलॉंग्स टू डब्ल्यू आय, देन डब्ल्यू इज इन्व्हेरियंट अंडर टी डब्ल्यू आय दिस वन. ओके, म्हणून म्हणतोय सगळे थेरमिक सारखेच दिसते. सो ई आय ऑफ अल्फा. ओके, काय होता ई आय तुमचा, इफ सपोज अल्फा बिलॉंग्स टू व्ही जर असेल तर व्ही आपण कसं अल्फा कसा लिहित असतो, अल्फा 1 प्लस अल्फा 2 सो ऑन, दिस इज अल्फा के, अँड ई ऑफ अल्फा इज इक्वल टू ई आय ऑफ अल्फा इज इक्वल टू अल्फा आय. तेव्हा असं होतं. इज इट करेक्ट?
Yes,
अँड
sir.
दिस वेक्टर बिलॉंग्स टू डब्ल्यू आय. तर हा काय होता है, अल्फा बिलॉंग्स टू v. So but here alpha belongs to wi, that means ei of alpha is equal to alpha here. Okay, so that means ei acts as on acts as an acts as an identity operator on कोणावर आयडेंटिटी सारखा ऍक्ट होतोय तो डब्ल्यू आय वर. इज इट करेक्ट? म्हणजे डब्ल्यू आयचा कोणताही वेक्टर घ्या, ई आय ऑफ अल्फा अल्फा सेंटर. ओके, एनी डाउट?
No. No, sir.
Okay, if alpha belongs to wi, ei of alpha is equal to alpha. That means ei acts as an identity operator on wi. Okay, so that means that is this element belongs to wi. That means ei of alpha belongs to what? Wi. Okay, that is equal to what? Range of ei. Okay, for this statement true for alpha belongs to w, and this statement is true for all alpha belongs to v. Okay, हा स्टेटमेंट कधी ट्रू होईल, फॉर ऑल अल्फा बिलॉंग्स टू v. ओके, v साठी आहे म्हणजे डब्ल्यू आय साठी तर असणारच आहे. दिस वन, दिस स्टेटमेंट इज ट्रू फॉर ऑल अल्फा बिलॉंग्स टू v. Why? ei is what? Range of wi, which is given to us. Okay, तुमच्या डब्ल्यू आय कुठे आहे, व्ही च्या आत आहे. ओके, इज करेक्ट? एनी डाउट?
No, sir.
Okay, so ei of alpha belongs to wi, which is equal to range of ei for all alpha belongs to v. Now consider, we have to prove that t into ei is equal to ei into t. No, ti of alpha belongs to wi. Okay, we have to prove that t of alpha belongs to wi. Now, so consider t of alpha. What is t of alpha? T of, what is the meaning of alpha? Alpha तुमचा आता कुठून आलेला आहे, wi. Okay, so this alpha we can write as an identity operator. Na, ei is an identity operator, act as an identity operator on wi. This is alpha. Is it correct? Instead of
Yes.
alpha, we write ei of alpha. So this is equal to t into ei of alpha. Okay, which is equal to, now t commutes, काय अजून केलंय, suppose ti et into ei is equal to ei into t, or assumption is ei into t of alpha. Okay, so this is equal to EI into T of alpha. Give it as an equation number 4. Okay, so this is what T of alpha. Okay, now since what is range of EI? Wait a minute. Range of EI is WI. Okay, therefore, therefore, this EI into T of alpha, okay, is in the range of EI. Na? This is belongs to WI. Is it correct?
Yes, sir.
That is, this EI acts as an identity operator on WI. So this is what T of alpha belongs to WI. Where all alpha belongs to WI. Okay, here we taken any arbitrary vector belongs to Wi and we get T of alpha belongs to Wi or all alpha belongs to Wi. That implies this shows that this shows that each Wi is invariant. Okay, invariant under T. Okay, any doubt?
No, sir.
कसा लगा लगा Okay, look at here one second. Suppose the linear operator T coordinates with each EI, that is T into EI is equal to EI into T. And we have to prove that this WI is invariant under T. Okay, so if take let alpha belongs to WI with any vector, and we are going to prove T of alpha belongs to WI. Okay, now then by the definition of EI on WI, what we get? EI of alpha is equal to alpha. Okay, for WI. All the elements belongs to WI. So this EI. Okay, असं सुद्धा ना तो अल्फा बिलॉंग्स टू जर बी जर असेल तर ई ऑफ अल्फा माझा अल्फा आय येत होता आणि हा अल्फा आहे कशात होता डब्ल्यू मध्ये ओके डब्ल्यू आय जर हाच तुमचा डब्ल्यू आय मध्ये घेतला असेल तर काय होईल मग हाच वेक्टर येईल नाही ते ओके पहा कसा इफ सपोज दिस अल्फा बिलॉंग्स टू डब्ल्यू आय ओके सो हा कशात कंटेंट आहे व्ही मध्ये कंटेंट आहे okay so this alpha we can write what is v w1 plus up to so on this is wi up to so on this is wk okay so alpha belongs to wi this vector hmm, how I can write 0 into alpha 1 0 into alpha 2 plus up to so on this is 0 into alpha I but alpha I म्हणजेच काय तुमचा alpha ना plus 0 into alpha k. Okay, if the alpha belongs to W, then what is T of E of alpha? Ith term, na? Sorry, 1 into alpha. Okay, so this is alpha. Is it correct? No?
Yes, sir.
Yes, sir.
Okay, so for alpha belongs to Wi, EI acts as an identity of the term. Okay, now consider T of alpha. T of alpha is equal to T into alpha is nothing but EI of alpha. T is commutes with each other, commutes with each EI. So this is EI into T of alpha. Okay, so what is T of alpha here? T of EI of T of alpha belongs to W. Okay, why? Because range of EI is WI by given statement. Okay, but EI of T of alpha, this EI acts as an identity operator. Okay, this EI of T of alpha is equal to T of alpha belongs to WI. Okay, any doubt up to here?
No, sir.
Okay, wait a minute. Okay, now the necessary part, necessary condition. Second, necessary condition. Okay, let us assume that Wi is invariant under T. Let us assume that Wi's are invariant under T. Okay, and we have to prove that T into ER is equal to ER into T, where I running from 1 to up to K. Okay, now we have this I is equal to E1 plus E2 plus up to so on K. How? Because this statement is given to us. Okay. Third one, such a statement. है ना? So I is equal to E1 plus E2 plus up to so on EK. Okay. So what is I of alpha? Is equal to alpha, which is equal to E1 plus E2 plus up to so on. This is EK of alpha. Okay, so this implies alpha is equal to E1 of alpha plus E2 of alpha plus up to so on. This is Ej of alpha. Okay, so this implies alpha is equal to summation I running from 1 to k ei of alpha. Is it correct?
Yes, sir.
So operating t on both sides. What we get? T of alpha is equal to T of summation I running from 1 to k. This is ei of alpha. Okay, so this implies T of alpha is equal to summation I running from 1 to k T of ei of alpha. Why? Since T is linear. Okay, any doubt?
No, sir.
Okay, now give it the question number 5. This is 4 and this one is 5. Okay, T of alpha is equal to summation of I running from 1 to k T into ei of alpha. Okay, now since Wi is what? Range of ei. Okay, therefore this ei of alpha belongs to what? Wi. Which one? This one. Okay, for I running from 1, 2, up to so on k. Okay, and also what we assumed here, Wi is invariant under T. That means T of ei of alpha also belongs to W, na? Okay, so this Wi are invariant under capital T. So therefore this T of ei of alpha belongs to
W.
Wi. Okay, why? Because this ei of alpha belongs to Wi and T is invariant under Wi. So this means the T image of ei of alpha also belongs to W. For I then from 1 to up to so on k. Okay, now हा वेक्टर कुठे आहे तुमचा? Wi. Okay, look at here. This one is Wi. Okay, this is T of ei of alpha. Okay, what is Wi? Wi is the range of EI. Okay, what is EI? EI is the projection on P. Okay, म्हणजे EI तुमचा एक linear operator exists तो या V वर. Okay, what is Wi? Wi is range of EI. Okay, म्हणजे the nature of this element is of the form. Okay, पहा मी नीट काय सांगतो. This Wi is range of EI. Okay, suppose this is the element. Okay, what is Wi? Wi is nothing but EI of beta for some beta belongs to V. Is it correct?
Yes, sir.
म्हणजे या पॉईंटसाठी या एलिमेंटसाठी इथे काय असायला हवा तुमचा पी इमेज असायला हवा दॅट इज बीटा. Okay, why? Because this element belongs to Wi. Wi is the range of EI. That means EI of beta is equal to T of EI of alpha. Is it correct? Okay.
Yes, sir.
This is not the part of the proof. Okay, फक्त समजण्यासाठी आहे. So here, this T of EI of alpha is equal to what? EI of beta. Okay, for some beta belongs to V. Is it correct?
Yes, sir.
या स्टेपमध्ये जेवढं स्टेप आहे की Wi is what? The range of EI. Hence, this implies T of EI of alpha is equal to EI of beta for some beta belongs to V. Give it as equation number 6. Now, using equation 6 in 5. What is equation number 5? Okay. T of EI of alpha is nothing but what? EI of beta. Okay, so put here. This is T of alpha is equal to summation I running from 1 to K EI of beta. Okay, so on equation 5 and 6. Is it correct? H value काय होती? EI of beta. Okay, so this is this one. Okay, for I running from 1 to 1 K. Okay, so operating EJ on both sides. Operating the next projection EJ on both sides. J running from 1 to up to some K. So what we get, this is EJ of T of alpha is equal to EJ of summation I running from 1 to K. 1 to yes, I running from 1 to K. Is it correct? So this one is EI of beta. Okay, now EJ is the projection on V. Okay, that means it is linear operator. So this is I running from 1 to K EJ into EI into beta. Okay, since EJ is linear. Okay, any doubt?
No, sir.
Okay, so now this EJ of E of alpha is equal to, now then I running from 1 to K. So what we get? EJ E1 beta plus EJ E2 beta plus EJ into EJ of beta plus up to some, this is EJ into EK of beta. Is it correct?
Yes, sir.
Now this is EJ of E of alpha is equal to, what is the value of this one?
0.
And this one is EJ square, not 1. Okay, 1 1 chalte, दोन्ही करो डेल्टा. Okay, so EJ square of beta plus 0 up to some plus g. Okay, but this is ej of t of alpha is equal to ej square of beta. But ej is what? Projection. That means ej square is equal to ej of beta. What is ej of beta? From 1. Okay, this is from 1 ej of beta. So we get ej of t of alpha is equal to ej of beta from 6. What is 6? E of beta is equal to T of EI of alpha. Put Ej into T of alpha is equal to T into Ej of beta from equation 6. Sorry, alpha. Okay, is it correct? From 6. EI of beta म्हणजे काय तुमचा T of EI of alpha. Ej of असेल तर काय असेल इथे Ej असेल. ओके ओके ते नोटेशन आहे फक्त Ej Ij. So this implies T into Ej is equal to Ej into T. Okay, where J running from 1, 2 up to so on. Okay, किंवा I घेऊ शकतो. Okay, hence T. Okay, any doubt up to here?
Yes, sir.
Okay, अजून एक थेरम आहे, 2, 4 ते 5 एक थेरम आहे, 2 definition आहे, primary decomposition theorem and invariant direct sum decomposition. आणि थेरम असे 3 अजून टॉपिक्स आहेत, मग त्यानंतर सेकंड चॅप्टर आहे सर. ओके, उद्या लेक्चर आहे का आपलं? असेल कदाचित. ओके ओके, एनी डाऊट इन दिस थेरम?
No,
न
sir.
समजण्यासारखं भाग काही नाही आहे, फक्त एकदा लक्षात केलं की येईल. आणि फक्त लिहायचं कसं यासाठी तुम्हाला प्रॅक्टिस करावं लागेल. ओके, एक थेरम 5 ते 6 वेळा लिहावं लागेल तुम्हाला जर परीक्षा ऑफलाईन झाली. ओके, एनी डाऊट इन दिस थेरम?
No, sir.
Okay, now tell me, if suppose I is the projection, sorry, E is the projection. E is what? Projection. Okay, notice करें. Note. Suppose E is projection on V. Suppose this capital E is projection on V. That is, E square is equal to E for all alpha belongs to V. Is it correct?
Yes,
Now,
sir.
if E is the projection, if capital E is projection on V, then I minus E, okay, identity operator minus E is also projection on V. Okay, I minus E, दोन ऑपरेटरचा सबट्रॅक्शन घेतलाय. Okay, it's also projection on V. How? If here we have to prove that R minus E is the projection on V. That is, we have to prove that I minus E bracket square is equal to I minus E. Okay. Okay, we have to show that I minus E bracket square is equal to I minus E. E हा प्रोजेक्शन दाखवायचा असेल तर काय प्रूव्ह करतो आपण? E स्क्वेअर इज इक्वल टू E. टी हा प्रोजेक्शन दाखवायचा असेल तर टी स्क्वेअर इज इक्वल टू टी. ओके, हे फक्त नोटेशन्स आहेत. Okay, so here I minus E, we have to prove that is projection on V. That means we have to show that I minus E bracket square is equal to I minus E. Okay, now consider I minus E bracket square. What is the value of A minus B bracket square?
Minus 2 EI.
I.
plus a square.
plus square, which is equal to I square is identity of letters I square. 2 into I into E. Okay. Identity into any of the letter is identity itself. So E is projection. That means E square is equal to E. I minus 2E plus 1E. So this is E. So that is here we get I minus E bracket square is equal to I minus. Okay. So hence I minus is what? Projection on V. Fill it out. Okay. Okay. So it is sufficient for today.